All right, yeah, thank you again for inviting me to give these lectures. So yeah, I'll talk about failed approaches to Hilbert's problem over Q. And by the way, you should all, I'm sure that some of you are much better at failing than I am. So you feel free to make suggestions. No, I'm just kidding. But if you have ideas, better ways to fail, then please let me know. Okay, so, all right, so let's see. So this is a reminder of Hilbert's 10th problem. The input is it's a decision problem where the input is a polynomial and many variables with integer coefficients, and the task is to decide whether there's an integer solution. So we're now going to consider Hilbert's 10th problem over Q, and the only difference is that we replace integers by rational numbers. It's most important to change it here. But, so we're looking for rational solutions now. All right, so how can you have? Suppose you're trying to prove that it's undecidable. So there are various approaches you could try. So any of the following would suffice to prove that the Hilbert's problem over Q is undecidable. So the first thing you could try is you could try to prove that Z is Diophantine in using polynomials over Q. So again, that means that there's some polynomial in n plus 1 variables, where the first variable you think of as a parameter, such that if you look at the rational values of that parameter, for which there exists a rational solution in the remaining variables, then the good parameter values for which it's solvable are exactly the integers. Okay, so that's it's the same definition as before, except with the variables running over Q. But you could ask for something weaker than this. Instead of getting Z literally as a subset of Q being Diophantine, you could try to hope for some other subset that's in bijection with the integers, but for which you can simulate the addition and multiplication of integers. And so sometimes this is called a Diophantine model. So let me give you a precise definition of this. Diophantine model of, I'll say of the ring Z, because I want not just a subset that looks like Z, but I want to have the operations as well. And using polynomials over Q. So what does this mean? So this means first of all, it should be a Diophantine set, so you can figure out what the elements are. So in a Diophantine way, so it's a Diophantine set. Let me call it S. And Diophantine, allow it to be a Diophantine in the general sense, meaning it could be in the rational points of some variety or some fine type Q scheme. So some X over Q, and it should be in bijection with the integers. There should be some bijection. Bijection phi from integers to S, such that if you look at so I want to be able to express addition and multiplication, and so the way you do that is you ask that the graph of addition and multiplication. When I say the graph of addition, I'm thinking of the set of A, B, C in Z cubed, such that A plus B equals C. So it's the subsets of Z cubed. And I want them, when you carry them across the bijection, they should correspond well, they're going to correspond to some subsets of S cubed, and then those are supposed to be Q Diophantine. Q Diophantine subsets of S cubed. Okay, so that's the sense in which you have sort of a copy of Z inside that's Diophantine and such that you can simulate, you can encode addition and multiplication. And so if you could do that, then you could again reduce, you could embed any instance of Hilbert's 10th problem as being a Diophantine question using equations over yeah. Sorry, the other way around. If you had an instance of Hilbert's 10th problem over Z, you could encode it as in terms of polynomial equations over Q in this way. And so you would prove that Hilbert's 10th problem over Q. If you had this, you would prove that Hilbert's 10th problem over Q is harder, at least as hard as Hilbert's 10th problem, the original Hilbert's 10th problem. And it's not, maybe it's not completely far-fetched that you could do this. Here's an example that almost does it. So this is maybe the first failed attempt. It's an almost example. So let's take an elliptic curve, and just to be explicit, let me take this one, for example. And yeah, so okay, and when I write this, I mean, elliptic curve is really supposed to be a projective curve. So I'm really supposed to take the projective closure of this in P2, which amounts, in this, for an equation like this, it just amounts to adding one point to infinity. Anyway, so and then there's an algebraic group law on this, and that gives the group of it makes the set of rational points into an abelian group. And for this elliptic curve, and it's a finely generated abelian group always. And for this particular elliptic curve, this finely generated abelian group turns out to be just free of rank 1. So it's just the multiples of a single point. And where P, well, okay, for this elliptic curve, there's some obvious rational points here, like 0, 1, and that turns out to be the generator. Okay, so there's an obvious bijection between these, and you can ask, okay, maybe I can use that as the phi. But it's not yet a Diophantine model. Yeah, so this map is just n goes to np. And now I have to make sure that the graph of addition and multiplication correspond to Diophantine sets. And for addition, it's okay because this corresponds to the graph of this. Well, okay. This is the addition law. This is the group law of the elliptic curve. Yeah. So in E of Q, and this graph. I mean this addition is this graph is going to be. This is Diophantine over Q. So it's defined using the group law, which is expressed in terms of some polynomials and rational functions and so on. So you can define this using the group law of E. Okay. Well, we're almost done. All we have to do now, we have to show that the graph of multiplication corresponds to something Diophantine. I mean, it does correspond to some subset, but nobody knows how to define it. I mean, this graph. I mean, the operation of multiplication on here corresponds to something rather weird over here. Yeah. It's the operation that sends, MP and NP to MNP. But that's definitely not given by just a single rational function or anything. But maybe there is some way to, if you had some auxiliary variables, you had some auxiliary equations, maybe you could find that relation. But nobody's been able to figure out how to do that yet.
There is an example where that is done for the function field over C into variables.
For function, okay. So for function field, So
Not
there are other fields where it has been possible to do things like this. Yeah. So okay. So Yeah. So okay. So so there's a third thing that's even weaker than a Diophantine model that you might hope to use, and so sometimes this is called a Diophantine interpretation. So okay, so this of the ring Z. Ring Z over using polynomial equations over Q. So by this I mean again there should be well, the difference between this and this is here you had you model Z as a Diophantine set. Here we're going to model Z as a Diophantine set modulo a Diophantine equivalence relation. And so yeah, so there's going to be a Diophantine set at S, and it's equipped with okay, so there should be a Diophantine equivalence relation. And there should be, well, okay, and then there should be a surjection from say P from S to Z, and such that inducing a bijection when you quotient out by the equivalence relation. So inducing a bijection from S, the equivalence classes to Z. And yeah, so and such that okay, and then so that's having an interpretation of Z as a set, but now you also need the operations, the ring operations on Z. So if you need such as the inverse images of the graphs, so you take the graphs of plus and times over here, the graphs plus and times. So under when I say the inverse images, I mean under the map from S cubed, under the surjection, the coordinate-wise surjection, that these inverse images of the graphs are Diophantine. Yeah. Okay. So because then again, if you had this, you could encode equations about polynomials over Z in terms of polynomials over Z. Okay. So yeah, but we don't know how to do that either. So I guess it's. Okay, so to help figure out whether it's possible to do these things, Barry Mazur made a conjecture. Well, okay, originally he called it a question. I guess he was a little bit nervous, so he called it a question first, and then after a couple of years, nobody was able to disprove it. And so then he said, okay, I think he then called it, okay, then it's a conjecture. But there's still very little evidence. Well, you'll see. Okay. Okay, so I'll just call it MC. Yeah. So what does this say? So it's a question about rational points and varieties. So if you have a variety over Q, and it's not so important what kind, whether it's anyway. You could do it for fine types. It wouldn't make much difference. Anyway, so what the conjecture says is that then if you take the closure of the set of rational points. So you take, okay, so the set of rational points is some countable subset. And it's a countable subset, and you can view it inside this sort of topological space of real points with the usual topology coming from real numbers. And then you can take the closure in that sort of Euclidean topology. For example, if X were affine space, then this would just be R to the n, and then we'd be taking the closure of Q to the n in R to the n, and well, Q to the n is dense. So then the closure would be the whole thing. But the general conjecture is that the closure has at most finally many connected components. So for example, if X were some hypersurface in affine space, then it's saying that it can't happen that the set of rational points is just a sequence marching off to infinity. That's an example of what this is ruling out. And yeah, and so in fact, I mean, it's pretty easy to see that, okay, so that's the conjecture. And it's pretty easy to see, and I mean, and this I think was the reason that Mazur introduced this, is that if you know this conjecture, then then somebody gives you a Diophantine set inside an X of Q, then this property for the set of all rational points implies the same property for the Diophantine subset. So it means that the closure of this inside X of R will have finally many connected components. And so why is this true? So maybe it's easiest to draw a picture. So you have, all right, so let's say, so first of all, Diophantine set by definition, to remind you, you have a morphism of varieties, so you have some big variety up here, and then you look at all the rational points on the big one, and you project them down. And the image, okay, so you have these. You have a bunch of points here. Yeah, and then the image points, when you project them down, that's the Diophantine subset. So this set here is S. These points here, that's the set of rational points of Q, and then the image is S. So I think it's maybe easier to think about the contrapositive of this. So suppose you know that S has infinitely many connected components. So you have like this component, this component, this component. Above each component, there's going to be at least one rational point. And they're kind of disjoint from each other. So those pre-images, above each connected component of S bar, there's going to have to be at least one component of Y of Q bar. And so therefore, if S bar has infinitely many connected components, then so will Y of Q bar. But if you know Mazur's conjecture for Y, then that's not possible. So then this Mazur's conjecture saying that Y of Q bar has finally many connected points implies that S bar also has finally many connected points. And in particular, if S bar has finally connected components, you can apply this to, if Z were Diophantine in Q, you could apply this to Z inside the affine A1 of Q. But Z bar does not have Z bar does not have finally many connected points. So this shows that Z, if this is true, if Mazur's conjecture is true, and you get this consequence, it shows that Z is not Diophantine. Yeah, so Mazur made this conjecture exactly. It almost seems like he was trying to spite the people who were trying to carry out this program of trying to find prove that Z is Diophantine. And in fact, what's even more annoying for the people who are trying to do this, okay, so you might say, oh, okay, Mazur rules out failed approach number 1, but maybe I can still do failed approach number 2. But then a little later, maybe a lot later, Günter Cornelissen and Karim Zahidi, they proved that it's even worse, that Mazur's conjecture not only rules out Z being Diophantine, it proves that there is not even a Diophantine model of Z over Q. This proof is a little, it's not too long, but it's a little trickier. Because the Diophantine model doesn't have to be discrete. It could be some weird subset that just happens to be in bijection. But the way the proof goes is that if you have this Diophantine model, so that means you can define this copy of Z inside Q, you can then use the Matiyasevich result to just show that every listable subset of that copy of Z is also Diophantine. And then you can find, inside that Diophantine model, you can select a listable subset that is discrete, either by having it a sequence tend to infinity, or else find some other limit set in your set and look at the points approaching that one. So that's the idea for that. Okay. So Maser killed off approaches 1 and 2, if you believe this conjecture. So well, there's still approach number 3, and so you can ask, okay, well, the natural question: does the Maser conjecture imply that also there does not exist a Diophantine interpretation? And I think this is an open question. So yeah. So anyway. So yeah. All right. So yeah. So it'd be nice to know whether this conjecture is really true or not. And so here are a couple of observations about this conjecture, and well, Maser already made these in his original paper on this. So first of all, the Maser conjecture holds for any abelian variety. And so how do you see this? So this is, there's not too much. I mean, all you really need to know to prove this is that, well, that this is a, in fact, you don't really need much of anything. So this is a subgroup of the real points. And so the closure of this is also going to be a subgroup. And so this is a closed, now you have a closed subgroup of the real points. And what do the real points of an abelian variety look like? I mean, this is just a Lie group. It's a commutative, connected, compact Lie group. And so it's just going to look like a bunch of copies of R mod Z, and then across some finite group. Okay, so, and now you can just use some topology, or Pontryagin duality theorem, or whatever. You can just classify, you can just describe what closed subgroups of a torus look like, and they all have finely many connected components. So just imagine, so this already implies that this subgroup has only finely many components. Okay, so that case is done. I didn't even need the Mordell-Weil theorem to do this. Yeah. So okay, another observation is that Maser conjecture holds for any x of dimension 1. So the proof of this is you can, well, okay, I'll sketch the proof. So first you can reduce to the case of you can reduce to the case where your curve is irreducible, and you can make it projective if you want. That's just adding a few points in most, so it doesn't really change the question. So reduce to the case of a smooth, you can desingularize it, because that also changes only things in a finite number of points. And so it's smooth projective, and you can assume it's geometrically integral, whatever that means. Okay, and then so a geometrically integral curve. And then and you can also, okay, well, obviously you can also assume that if you're trying to prove this conjecture, you can also assume that there is a rational point, because the empty set has at most finely many connected components. So then you can just go through the classification of curves according by genus. And so there's the usual trichotomy where you have genus, you have genus 0 curves, genus 1 curves, and then genus many curves. So genus 0 curve with a rational point, this is just the projective line. And well, then it's just true because the closure of P1 of Q and P1 of R is just the whole thing. One connect each one. In this case, X is if it's a genus 1 curve with a rational point, that means it's an elliptic curve. But an elliptic curve is a special case of an abelian variety, which we just already did. So this is done, this is also done. And again, you don't even need the Mordell theorem. So okay, for the last case, you do need to do something. So there's a genus. If you have a curve genus at least 2, then it's okay. Well, it's very easy to prove this if you assume a difficult theorem that says that their set of rational points is finite in this case. So that's Fulton's theorem. It's the one we got the Fields Medal for. So, but anyway, once you have that, then well, it's true. If you take the closure of a finite set, it still has finally made connected points. So yeah. So okay. So that does the case of curves. So okay. So we did all the way up to dimension 1. Yeah.
Sorry. Or this observation says that the graph of multiplication in almost example is not Diophantine, because MC implies there is no Diophantine model.
Sorry. Say it again.
The dimension of X.
This is for arbitrary dimension.
So to say that I mean we are using only elliptic curve in that case, and even in that case we need the higher dimensional case to rule out the.
Oh. Well, okay. For this, maybe this is when you're if you're trying to prove that Z is Diophantine. If you want to use Mazur's conjecture to rule that out, to carry out this, you have to apply Mazur's conjecture not to the A1. You have to apply it to the variety upstairs that's dominating A1, or that's mapping down to A1. So I guess. Okay, but I guess this argument shows you can't just have a curve whose rational points map down to Z, for example. But okay.
So I guess that rules out almost example because then we're using the curve E.
No, but the multiplication can be defined in a very difficult way with a high dimensional.
That's true.
Yeah. So it's not quite clear. Yeah. So.
Yeah, you're right. Sorry.
So I think there's still hope for almost example.
Since when has the almost example been studied?
Since when?
Yeah.
I think the idea for this probably has been around for a long time. I think because I don't know who first thought of trying to do this. It's probably something like Denef or Vedas or something.
Denef in the 70s used exactly this to tackle RT or
yeah, so Denef was using elliptic curves for similar problems. So I'm sure he was aware of this kind of thing. Yeah, but I know that Vedas also worked on this somewhat. Tried to turn this almost example into thing. But yeah, so probably at least since the 1970s. So okay.
Quite a long time.
Yeah, but so was the Denef-Lipschitz conjecture, and that got solved. So yeah, okay.
So what about MC conjecture for surfaces?
Okay, yeah, that's a good question. So yeah, so we did all the way up to 1 dimension, and then you might ask, okay, how much progress? This was all done 30 years ago. What progress has been made since then? And the answer is essentially none. So yeah, so not much else is known about this conjecture. So I mean, I think this is kind of also part of the reason. It's almost also like as if Mazur was trying to embarrass the whole field of arithmetic geometry, showing, oh, you can't even do that. You can't even figure out a basic question like this, even for like 2-dimensional varieties. You can't even figure out. I mean, I think what all this shows really is that number theorists don't really know anything about rational points on higher dimensional varieties. They know almost nothing. So And so we don't. I mean, I think people don't even have a consensus as to whether this should be true or not. I mean, I kind of lean towards saying it's not true, but I don't know. I think it's really unclear. Okay. Yeah. So so that's where things stand with that. So let me mention some other. Let me sort of change topics a little bit now, and talk about the function field analog. So in the function field analog, okay, so here when I say function fields, I'm talking about global function fields. So these are finely generated fields of Kronecker dimension 1 that are of characteristic P. So that means they're going to be transcendence degree 1 over a finite field. And for Fedas's original result, he took this kind of, just the simplest kind of rational function fields over a finite field, where you just take the rational functions in one variable. So the quotient ring is the fraction field of the polynomial ring. And also, just for some simplicity, he assumed Q is odd. And then you can ask the question, Hilbert's 10th problem over this field, which is, and this is supposed to be, this is analogous to a number field, so you might expect this to have the same answer. And he succeeded in proving that this one was undecidable. So yeah, and after that, in a series of papers, this was later generalized to all global function fields. So you mean dropping this assumption on the field, but also allowing finite extensions of these, so which would be function fields of higher degree curves over a finite field. And so this is by okay, series of papers. Videla, Schockenbach. Yeah, okay, Carlos Videla, Sascha Schockenbach, and Kirsten Eisenträger. Okay, and it's also been generalized to higher Kronecker dimensions. So you can have function fields in many function fields of varieties over finite fields, and that you can do too. Okay, so but let me just go back to Fedas's original thing. Maybe I'll just say a little bit about the outline of one possible proof of this. Okay, so it's going to be again. Okay, I'm going to have to skip a lot of details, but let me just. Yeah, okay, so it's one of these multi-step proofs again, and so I'll have to. But in the meantime, are there any questions?
Are there specific families of surfaces for which MC is known?
There are some things that are known. Okay, I guess I already said for abelian surfaces, for abelian varieties, if they're two-dimensional, you have it for those. Yeah, I don't remember. Actually, I don't really remember if there's much. Well, okay. I mean, I guess there's some easy cases like P2. It's true for Pn. But I guess anything that's, anything that's birational to Pn, because then the rational points will be dense, even in the real points. But yeah, but I'm not sure. Yeah, I forgot to.
Sorry.
What? Yeah, but I can't remember. I think there might be some sparse, very few results, but I don't think much is known. I think even for like things as simple as like cubic surfaces, I'm not sure if it's known for those. I can't remember. I think maybe it's true in that case because you have. Oh wait, sorry. I think in that case it is known. Sorry, yeah, because there's some varieties for which once you have one rational point, then there you have a actually the Zizki, and you have enough. You have constructions that you can use to generate other ones. Okay, I can't remember offhand. Yeah,
so
it's a question.
if Q is 2, then it's decidable or undecidable?
Or Q equals 2. Oh no, it's still undecidable. So it was, when I say generalized, I mean that that's what Videla did. He did it for characteristic 2, and then chop it up and figure generalize it to other genus function field. Okay, so all right, so okay, I'm doing the outline of the proof. So first, the first step is to find we're going to look at some hyperelliptic curve. So we're going to find some polynomial such that when you look at the curve, well, you take this hyperelliptic curve. So if f were degree 3, this would be elliptic curve, but once it gets up to degree 5 or higher, it'll have higher genus. That's hyperelliptic curve. But actually, let me take a quadratic twist. So these are the constants. Yeah, these are the the field is fq adjoint t. So let me put a number in front of this y squared. So f of t. So t is just an element of the ground field. Yeah. So this is just some element of the ground field. And so this is sometimes called the quadratic twist of the curve. But the reason for putting that there is that once I do that, I call this y, then there's some obvious k rational points on this. For example, if I take, what's the most obvious one? If you take x equal t and y equal 1, that works. Can anybody think of another one?
Equal or minus 1.
Yeah, very good. Okay, so you get just a plus or minus 1. Does anybody see another one? So I mean, there's a trick here where this thing is actually over the field where you have a square root of f of t, you can absorb that into the y squared, and so over that field it becomes this thing, and then if you have any solution to this, well, f has coefficients in fq. If you have a solution to this, you can raise x and q y to the qth power, and then because that's and then so any solution of this will give rise to a new one where you raise things to the qth power. And you can iterate that to get an infinite sequence of solutions. Now, and then you can carry them back across this equation to get a point here. And it turns out that even though this process going across here is not defined over k, when you do this, you actually come back to something that is defined over k. And so if you do this, for example, so there's going to be a solution here where you have t to the, let's see. Oh, I guess. All right, well, okay, so I guess there's t. Okay, I'm a little bit confused about whether I'm allowed to. I guess I can't take p powers. I think I really need, p. So anyway, I think I want. Okay, let me just do this for p. I'm just getting a little worried about. Let's assume, just for today, let's assume q equals, it's just a prime, not a prime power. So then I can take p powers, and then if you work it out, you'll see that you can just plug this in and see that it works. Maybe it's not completely obvious. Well, if you think about it a little bit, I think you'll see that it works. And then you can keep going. So you have t to the p squared, and t to the p squared minus 1 over 2, and so on. And so you get this infinite set of solutions. And you can show that if you choose f such that this curve has no non-trivial automorphisms besides the hyperelliptic involution, then you can show that the set of rational points is exactly this up to a finite set. And then using this, by then projecting onto the first coordinate, you can prove, so this is step 2, you can prove that the set, you get that this set is Diophantine over this. And you might think, oh, that's nice. Maybe I'll use this as my Diophantine model of the integers, or at least of the natural numbers. But that's not exactly how it goes. But it's just, the next step is to prove that the whole relation that says that that y is a p to the nth power of x, where x now and y are both variables. To say that this holds for some n. So this, where n, so this is a Diophantine relation. Yeah, and when I say this, I mean I'm taking sort of the union of the graphs of these things for all n. Yeah. So okay. And then what's going to happen is if you take, we're going to use a valuation on this field, so the t-adic valuation, and let this be the valuation then for of the t-adic valuation, which is going from k to, and that's a discrete valuation, measuring the order of vanishing at the order of the rational function at 0. And so if you take the non-zero elements of that valuation ring and you quotient out by the unit group, then so quotienting by the unit group means that you're forgetting everything about the number except for its valuation. So the valuation defines a bijection between this and natural numbers. And then this defines a Diophantine model of the following structure. You have the natural numbers. You can talk about zero. I mean, ideally you would have addition and multiplication defined in this model, but it's not easy to define addition and multiplication. Like, how do you say if you have something of valuation m and something of valuation n? How do you get something of valuation m times n? That's not obvious at all. I mean, if you multiply, you add the valuations. So it's easy to get plus. But what you can get using this is you can get a different kind of relation. You can get this weird relation that Vedas calls divide sub p, where this means, it's probably what you think it's going to mean. It means that for two natural numbers, x sort of p divides y means that y is equal to p to the n times x for some n, for some n, natural number n. Okay, that's what you can extract from 3. Okay, so now you have this funny language and funny structure. So you have these funny operations you can do, and then the next step is now you just forget about the function field completely. You just hack around using these things. See what other sets you can build using the positive existential theory of these. And then you show that using these, you can actually, so Vedas figured out a clever way to express multiplication in Diophantine in this language. And so once you have that, then now you have natural numbers with addition and multiplication, and so now you can just use Hilbert's sum problem. So now you've reduced it to Hilbert's sum problem over Z, and so you've encoded Hilbert's sum problem over Z in the function, in the arithmetic of this function field. And so that's how it goes. All right. So good. So I guess So okay. Any questions about this? That's all I was going to say about that. Yeah, but unfortunately, I mean, So I mean, another hope you could say, oh yeah.
I guess I just wanted to make two remarks in that sort of, I mean, this theorem doesn't, I mean, that isn't the end of the story, in that there's still some open questions you could ask, namely, how about Hilbert 10 when you don't allow the parameter t, right? I mean,
yeah, okay.
T is very much allowed here. What happens if you only look at equations not involving t? I mean, that just work over the prime field. Is that undecidable? And the other is the DPRM theorem true? I mean, is every semi-decidable set Fantine over this sort of function field? And I don't think we know that either.
Yeah, well, I think the first question I thought was, maybe I'm misremembering, but I thought the first question was already...
If you don't allow t, then you get a decidable thing, at least in the FPT case, because you have a solution if and only if you have a solution over FQ.
That's not true that's true in the polynomial ring, but not in the rational function field. I mean, you can say you have infinitely many elements.
Yeah.
Okay, I don't remember, but those are good questions. So yeah, yeah. I'm trying to remember. Oh, I mean, I'm trying to remember. What did Jeroen de Meyer did something?
I mean, he did it over the polynomial ring again.
Oh, he did. He proved. He worked in the instead of in the field, he had the FP something like FQ bracket T, and then he proved that all the listable sets were identical.
As I say, to the best of my knowledge, both of these questions are still open, and I'd be very interested.
Okay, all right, something to do. Okay. Yeah, all right. So, yeah. You said you had two comments. So you made them both. Okay, good. Yeah. Anybody else? Yeah.
Yeah. Are there any like ways of modeling multiplication? It seems like we can do addition, sort of. Has anybody found?
Wait. So the model. What do you mean?
Like.
I mean, here he made us figure out how to model multiplication using like.
Yeah, sorry. I mean,
in terms of these operators, he found some clever way to do it.
Yeah, I guess I mean, not in this case, but like in the almost example, and in this case, it was like, oh, we're able to. There's like a natural way to.
You mean the elliptic curve? Rational points
So
in the beginning.
You've shown us two examples where it's like, oh, like getting addition is like pretty not hard,
yeah.
But then like the multiplication, like, is there any case where like we kind of
Multiplication is done and addition is not?
Oh, you're asking that? What you're asking?
Yeah, basically.
Case where where it's obvious how to do multiplication, but nobody knows how to do addition.
Yeah.
I don't know. I mean, yeah, I'm not sure. Yeah. Okay. Anyway, so yeah, but I mean, going back to the almost example. I mean, I personally I feel as if our best hope for getting Hilbert's 10th problem over Q is to take that almost example, the elliptic curve over Q, because all you need, if you can just show that inside that copy of Z, and we already have addition. Maybe if you can just put in some extra equations to cut out some subset of, I don't know, E of Q cross E of Q, just find any new Diophantine relation. That'll give you some extra operation or to throw into your language. And I mean, here, even something as weak as this, just knowing this one number is a power of P times the other one, that was already enough to get no multiplication. So maybe if you can just figure out one more interesting operation, then that would do it. I don't know.
Inside the elliptic curve.
What?
In the
elliptic curve, in the original almost example. Yeah, that would be. I mean, if you told me that I had to. I mean, I don't know. Yeah, if you told me that you were gonna. Yeah, that the only way for me to save. Yeah, I mean, this is like an Erdős question. If the aliens came and said they're going to destroy the Earth unless you prove Hilbert's 10th problem over Q is undecidable, then I would probably start trying to do the almost example. Okay. Yeah. All right. So let me end just by by talking about going back to the problem for Q. And just say some things that are known. So first of all, maybe I should say, maybe we mentioned this already, but Julia Robinson in 1949, she didn't prove that Z is Diophantine in Q, but she did show that it's definable by a first order formula. So it's first order formula, first order definable in Q. Yeah, I guess that's what definable means, first order. And so this means that it's cut out. There's a formula with one free variable where if you let the variables run over the rational numbers, then the values of that parameter, of that one parameter for which this formula becomes true, is exactly the integers. And the type of this formula was like a for all there exists, for all there exists, if you look at her original proof, where each of these represents multiple copies of the same kind of quantifier. Yeah? So I guess what would this, is this pi, what is it, pi 0.04? Okay, I always forget how the counting goes. Okay, so pi 0.4 formula. Yeah. Whereas Diophantine would mean you have all you have are existential quantifiers. That's what you want for Hilbert's to prove that Z is Diophantine. And so, okay, so there's a game now. You just try to, how many of these quantifiers can you get rid of? And so, yeah, so I started playing this game. I got it down to, I had some argument using Quaternion algebras where I could, again, prove it's use the first order formula, but I got it down to, I guess this would be pi 0.2. So so just a for all. What? What do you say?
No, how many existential ones?
Well, my formula has. I mean, who cares? It's still pi 0.2. So there, it was this kind of formula. Yeah, so it's pi 0.2. Yeah, that's because we're only counting the number of alternations. Well, maybe you do care about how many. Well, I mean, you don't really care about these. What you really want to get rid of are these, because all you have to do, just two more quantifiers you have to get rid of to get proof to get Hilbert's 10th problem over Q. And yeah, Königsmann then, sort of building on my work, he managed to get it. He managed to get rid of one of those, so he got like. I think he had a lot more of these, but who cares? I mean, the point was to get rid of this thing. Yeah, and maybe I should say, by the way, all these things have been, you can generalize to number fields. So this last one was done by Jennifer Park to generalize this one to number fields. Yeah, so, and moreover, I can also tell you.
He just said so, universal.
What?
He just said universal, right?
Yeah, he also did a formula that was like this.
Yeah.
I'm not sure if that's better, or I don't know. I don't know. It's just different, I guess. I mean, if you're trying to get rid of all the universal quantifiers, you got rid of the wrong kind of quantifier. So, but okay. All right. So let me. Any questions about this? So I mean, people have been stuck on this now. So nobody's gotten rid of that last quantifier. I guess I think there's a paper that took. Well, that got reduced in that long sequence of Königsmann thing. I think Nicola Dans, he wrote a paper where he got it down to some reasonable number of quantifiers. I forgot exactly the number.
I mean, it's like 12.
Yeah, something like something. Yeah, I was like, I think Königsmann in his original paper he had like 400 quantifiers or something. Except I'm not even sure if he. I mean, I don't know. I mean, when the number gets that big, I mean, can you really trust the number that's that big? I don't know.
Maybe we need Lena.
Yeah, well, okay. So, let's see. Yeah, anyway, so that approach, those approaches haven't quite worked yet. But the proofs, I mean, Koenigsmann's proof is also kind of interesting. It uses quadratic reciprocity. And I mean, I was already using quaternion algebras and local global, I mean, well, Julia Robinson, I mean, all these proofs use some number theory. Julia Robinson was using the local global principle for quadratic forms over number fields. And yeah. Okay, anyway. Okay, so maybe the last thing I'll talk about is just what do we know about some, what sets do we know are Q Diophantine? I mean, ideally, we would want to get Z being Diophantine, or at least some Diophantine model. And so let me just list some. I mean, because the nice thing, well, once you build a Diophantine set, you can use that. You can add that to your library and use that in further Diophantine definitions. So you could hope, you just hope you build up enough sets, then you eventually find one that eventually find Z or something like that. So you can, okay, so this is the localization of Z at the prime ideal P. So concretely what this is, it's a set of rational numbers such that the denominator is not, there's no P's in it, there's no prime P. The prime P does not appear in the denominator. And so for any prime P, Julia Robinson showed that this was definable by using quadratic forms. Yeah, so I mean in fact, this is how she got Z being first order definable. Because if you intersect this over all P, then you're saying you're looking at rational numbers where no primes are allowed to appear in the denominator. So those are just integers. And so, but that requires a for all quantifier to take the intersection. And so, yeah, so that's, okay, so in my, so another one that's been proved a while ago, I showed that if you take the non-squares, all the rational numbers that aren't squares, then that's Diophantine. I don't know if that's good for anything, but anyway. I mean, the problem with all these sets is that they're too big. They're too close to being all of Q, and you really need to cut down it to something that's, small, something that's closer to integers.
Yeah.
Yeah, and this was generalized by, oh, I think I forgot to write down this. Okay, and I forgot to write down the authors for this. I think it was Koyutolen. Oh, sorry, I'm really sorry. I forgot. There's somebody else, I'm pretty sure.
Jan van Geel.
Oh, Van Geel, that's right. Okay, you know what I'm talking about then. Okay, good. So they generalized this to, yeah, by the way, my proof of this was kind of complicated. I used a Brouwer-Monnian obstruction. I used a family of varieties where I could use the Brouwer-Monnian obstruction to knock out the rational points on some of the varieties of the family. And then this was generalizing that, I think. But Koenigsmann, in his paper, he also found a simpler approach to these things. And he was able to prove some additional things. So, okay, so we already said that he could prove that the Z was definable with a for all 400 times, for all. And so if you take the complement, then that means that Q, the non-integers, that's a Diophantine set. So that seems really close to proving that Z is a Diophantine set, but unfortunately, this doesn't seem to be good for anything. Again, it's a set that's just too big. It doesn't seem to be. It doesn't seem to be. Yeah. He also proved that that if you take the non-norms, so if you have a field extension, a quadratic extension. If you have a quadratic extension, you take all the numbers that are not norms. So, for example, you take all the rational numbers that are not of the form x squared plus y squared, for example. Those would be the norms from Q join I. You take all the rational numbers that are not sums of two squares, and that's a Diophantine set. But yeah, but again, this is again a really large set, though. Yeah. Maybe I can also mention. Okay, yeah, there's also Philip, Guzman. Okay, so I'll state the one variable version of it, but what he proves is also it for many multivariable polynomials. And also all these results, you don't need to do it for Q. You can generalize all these things to number fields. Yeah, or even global fields. So all right. So you can ask about. So you can ask about the tuples of rational numbers that make this polynomial irreducible. I mean, generically, most polynomials are irreducible. So this is kind of a large subset of Qn plus 1. Yeah. So that's another thing. Yeah, and as I said, and likewise for multivariable polynomials. Multivariable. Actually, I can't remember. Maybe somebody in the audience can remember. Has this been generalized to arbitrary fields? Does this follow?
Morrison.
Yeah. Okay. He did it for cyclic, right? Or did he do it for all number fields?
I think it's only for cyclic.
I think I remember Morrison. Okay, Travis Morrison did I think Q.
I think he does numbers.
Yeah, I think where QK is Q joined like an mth root of some rational number.
Yeah, it doesn't need to work over Q. I mean,
Yeah. I'm only doing it over Q though. Yeah, so all these things, all these things can be generalized number. But for other number fields, is it still open? I can't remember.
Not cyclic, you mean?
Yeah.
That's wide open. Nobody has any clue.
Okay, that's enough. Yeah. Okay, well that's another possible problem to think about. But I mean, again, these are all large sets though, so it's not exactly clear where to go from here. So, all right. So unless other people have other failed approaches, maybe I should stop here. Yeah.